Hello and welcome to 2.7, the derivative as a function. So far we've considered the derivative as a function using the limit notation. Okay, we're going to change our point of view and let our function vary slightly. Instead of having f of a in our formula for the derivative, we're going to use x. Okay, we're going to replace a with x, the variable x, and then we're going to use this new version as our derivative function. Okay, so let's take a look. So given any number x for which the limit exists, we assign x to the number f prime of x. Okay, so we could regard f prime as a new function and we call it the derivative of f. Okay. So the function f prime is called the derivative of f because it has been derived from f with the limiting operation in equation 2. Okay, the domain of f prime is a set x such that the derivative of f prime of x exists and may be smaller than the domain of f. Okay, so let's take a look at an example. The graph of a function f is given below. Use it to sketch the graph of the derivative f prime. Okay, so one thing we're going to make note as we look at this derivative. Okay, notice how we have certain spots where we could draw a horizontal tangent line. Right, we could draw a horizontal tangent line at these turning points. So that tells us at those points the slopes are going to be 0. Okay, so when we go to graph the slope function at those points, we should expect a slope of 0. Okay, now to go from this 0 to this one, we should expect some kind of positive and a negative trend, okay, in this region. And then to go from this 0 to this 0, we should expect some kind of negative trend followed by a positive upward trend. Okay, and then from this point on, we would expect a positive trend. Okay, so let's take a look at what the graphs would look like. Okay, almost like a side by side. So notice this bottom graph is the graph of the derivative function. So like I said before, we have a 0 at this point. Okay, we called it A, now it's A prime. At B, we have another 0 horizontal tangent line. So again, B, we get another 0. At C, we have another horizontal tangent line where the derivative is 0. So again, that matches up. Okay, and then afterwards we go upwards like that. Okay, so generally that's the trend. In between zeros, you'll usually see some kind of increasing followed by decreasing, or decreasing followed by increasing. Okay, and that'll be due to what we call concavity, which we'll learn later on in the course. Okay. Okay, another example. Derivative of a function given by a formula. If f of x equals x cubed minus x, find the formula for f prime of x. And then illustrate by comparing the graphs of f and f prime. Okay, so let's take a look at the formula for f prime of x. So we're going to find the derivative. Okay, we'll use our derivative formula involving the limit. Okay, so we would say limit as h approaches 0 of f of x plus h minus f of x all over h. So for our purposes, looking at our function, x cubed minus x, first we're going to plug in x plus h everywhere there's an x. Then we're going to subtract the original function, x cubed minus x, divided by h, and then we'll apply the limit, and we'll see what we end up with. Okay, so let's do the f of x plus h first. So that means we would have x plus h cubed minus x plus h minus the original function which will be x cubed minus x. Okay, so we need to expand on the x plus h cubed. Okay, so let's do that. Let's expand. Maybe let's do a new page and we'll expand it there. Okay, so x plus h cubed, that's going to be x plus h times x plus h times x plus h. Okay, so what I'll do is I'll FOIL two of these first, so that'll give me x squared plus xh plus xh, that's 2xh plus h squared. Okay, multiply that times x plus h. Okay, so now distribute the x. So that'll be x cubed plus 2x squared h plus xh squared plus, this is h times x squared, so that's going to be x squared h plus 2xh squared plus h cubed. Okay, so lining it up this way allows me to just add vertically. So I have x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, so that's my x plus h quantity cubed. Okay, so let's go back. Let's put that in. Plus 3x squared h plus 3xh squared plus h cubed. Okay, distribute the minus in here, so minus x minus h. Distribute the minus into here, minus x cubed plus x. All over h. Okay, so now let's see if anything cancels out. We have x cubed and a minus x cubed, that's gone. We have a minus x and a plus x, that's gone. Anything else? I think that's about it. Okay. So we have limit h approaches 0. I have 3x squared h plus 3x h squared plus h cubed minus h. 3x squared h plus 3x h squared plus h cubed minus h. Okay, so what will happen next, I notice there's a common h in the top. I'm going to factor that out. Okay, so I have 3x squared plus 3x h plus h squared minus 1. And then when I factored out that h, I can now cancel with the h in the denominator. So now I'm left with limit h approaches 0 of 3x squared plus 3x h plus h squared minus 1. Okay, so now if I apply the limit and I plug in 0, right, just plug in a 0 and plug in a 0 here, that means these terms will go to 0. So I'll be left with only 3x squared minus 1. And that will be my formula for the derivative. Okay, now comparing the graphs of our function with our derivative function, let's take a look. Okay, so here's our function. Okay, it's a cubic. Okay, and here's our derivative function. Okay, notice the two places where we have horizontal tangent lines. Okay, right here and right here. Those would correspond to these 2 points where we have the zeros. Okay. Okay, so let's take a look at our next example. If f of x equals the square root of x, find the derivative of f, state the domain of f prime. Okay, so let's find the derivative of f. Okay, so using our same limit definition, we would have f of x plus h minus f of x all over h. Okay, so for our function, we would have the square root of x plus h minus the square root of x all over h. Now to help us simplify this, we're going to multiply by the conjugate of the numerator. Okay, because right now when we plug in 0, we get the undefined case. We don't want that, right? So we're going to multiply by the conjugate of the numerator. Okay, so this will be multiplied by square root of x plus h plus the square root of x over square root of x plus h plus the square root of x. Okay, so when we multiply the square root of x plus h times square root of x plus h, that'll just give us x plus h. And then the middle terms will cancel. Square root of x plus h times square root of x, and then minus square root of x times square root of x plus h. A positive times a negative, square root of x times square root of x will be a negative. Square root of x times square root of x will be x. Okay, denominator will be h times square root of x plus h plus the square root of x. Okay, so when you see this, now next step is you simplify. You have x and a minus x. They will cancel. So you're left with h we have h over h times square root of x plus h plus the square root of x. Okay, we can cancel h and an h, so that leaves us with the 1 on top. So limit as h approaches 0, 1 over square root of x plus h plus square root of x. And now we could apply the limit, plug in 0 for h. Square root of x plus 0 is just x. So we have 1 over square root of x plus square root of x, which will give us 1 over 2 square root of x. Okay, so this will be our derivative function. 1 over 2 times square root of x. Okay, so now looking at the second part, it says state the domain of f prime. So, well, the domain here, we could put any number as long as, in fact, because it's a square root function, we can't have square root of negatives, right? And we can't put in a 0 in there because that'll make a denominator of 0. Okay, so no negatives, because we can't have square root of negatives. Okay, cannot put 0 there, even though we could do square root of 0 and get 0, but we can't have square root of, we can't have a denominator of 0 in this case because it's a fraction. So that means our domain then for f prime will be not including 0, so we'll do interval notation 0 to infinity, and we got parentheses. Okay, and that would be it. Okay, find f prime if f of x equals 1 minus x over 2 plus x. Okay, so we'll use the same definition of the derivative. Limit as h approaches 0 of f of x plus h minus f of x all over h. So this would be limit as h approaches 0. Plug in x plus h, so we would do 1 minus x plus h over 2 plus x plus h minus original function 1 minus x over 2 plus x all over h. So we're going to try to simplify the top. We have two denominators. Our least common denominator will just be the two denominators multiplied together. Okay, so 2 plus x plus h times 2 plus x. Okay, so we'll multiply top and bottom by that denominator. Okay, so first what I want to do is I want to simplify the parentheses. I want to have extra parentheses there when I don't need them. Alright, so I'm going to take this moment to just simplify that. What I'll also do, because I don't want to have this complex fraction looking thing, is this divide by h is the same as taking 1 over h, and we're going to multiply by that numerator. Okay, so instead of having a divide by h, I'll pull it to the side here and I'll say 1 over h times, and I'll have my numerator piece in here. Okay, so if I have without my parentheses, I'll have to distribute the minus in here. Okay, so I'll have 1 minus x minus h. Okay, and I'll leave a space. Minus, and then 1 minus x. And then the denominator would be 2 plus x plus h. Okay, so now we multiply by the missing piece of the denominator, right? So the first fraction, you're missing the 2 plus x. So I'll multiply top and bottom by 2 plus x. Okay, the second fraction, we'll multiply that one by 2 plus x plus h. Okay, so let's put this all under one fraction then. So we'll have 1 minus x minus h times 2 plus x minus 1 minus x times 2 plus x plus h all over h from our 1 over h times 2 plus x plus h times 2 plus x. Okay, so we're going to have to expand on both of these numerators. Okay, so let's do that. I'll take some space over here to do that. Okay, let's expand on it. First we'll do it this way. 2 times 1, 2 times negative x, 2 times negative h, and then we'll distribute the x the same way. Okay, so we have 2 times 1 is 2, minus 2x minus 2h, and then x times 1 is x, minus x times x is x squared, minus x times h is hx. Okay, we got the minus in between. We'll put the second part in parentheses. 1 times everything in the second parentheses, then negative x times everything in the second parentheses. So 1 times 2 is 2, 1 times x is x, 1 times h is h. Okay, negative x's turn, negative 2x, negative x squared and negative hx. Okay, denominator should still be the same. Okay, so can we combine anything? Let's see, let's take a look. We have a lot of things we could combine, it looks like. Let's see, we have, if we distribute this minus, yeah, let's do this. Let's do negative 2x. Probably better if we keep it the same way it is, but then we'll just distribute that second half minus. You could combine like terms. Okay, so then we're going to do minus 2 minus x minus h plus 2x plus x squared plus hx. Okay, so now what cancels? A lot of things should cancel. I see 2 and negative 2, negative 2x and a positive 2x. What else? A plus x and a minus x. Minus x squared and a plus x squared. Minus hx and a plus hx. Okay, so all we're left with is a minus 2h and a minus h, which simplifies nicely to a minus 3h. So we have minus 3h over h times 2 plus x plus h times 2 plus x. Okay, cancel out h's from top and bottom. Okay, those two will be gone. So we have limit as h approaches 0 of negative 3 over 2 plus x plus h times 2 plus x. And now we could apply the limit, plug in 0. Okay, so we have negative 3 over 2 plus x times 2 plus x, which is negative 3 over 2 plus x quantity squared. Okay, and that would be it. Okay, other notations for the derivative. Okay, you'll see f prime of x, probably more common than the other ones. You'll see y prime. You'll see dy dx. Okay, these are probably the three more common notations. Then you'll see df dx, d dx of f of x, capital D f of x, d with a subscript x of f of x. Okay, derivative with respect to x of f of x. Okay, the symbols d and d over dx are called differentiation operators. They indicate the operation of differentiation, which is the process of calculating a derivative. Okay, dy dx, again one of the more popular versions. This notation was introduced by the mathematician Leibniz. Okay, and it's just another way of saying f prime of x. Okay, very useful and suggestive notation. We can write this in the form delta y over delta x, limit as delta x approaches 0. Okay, if you want to find the value of the derivative in Leibniz notation at a specific number, then we use this notation. dy dx, vertical bar, and then you're evaluating the derivative at a. Okay, or you could have a different version of that vertical bar, dy dx, it's like a big square bracket, x equals a. Okay. Otherwise, you could just write it like this, f prime, and then a in parentheses. Okay, definition, a function is differentiable at a if the derivative at a exists. Okay, where is the function f of x equal to absolute value of x differentiable? Okay, so for absolute value of x, we have to consider two versions of the derivative. Right, you could have a positive x or you could have a negative x. Right, so for the case if you have a positive x, if x is greater than 0, then we know that absolute value of x is just equal to x. Okay, so when we go to do our definition of the derivative, this is what we would have. Okay, so we have limit as h approaches 0. Now absolute value x plus h is just going to be x plus h. Absolute value of x is just x. Okay, x minus x, these cancel. So we're left with limit as h approaches 0 of h over h, which is just 1. Okay, so that would be our limit. That would be our derivative when x is positive. Okay, let's do when x is negative. So if x is less than 0, then we know that absolute value of x is going to equal negative x. Okay, so that means limit h approaches 0 of absolute value x plus h minus absolute value x over h. This will be, when it's the negative version, we could do like this, minus so we would just replace absolute value x with negative x. Okay, distribute the negatives, so negative x minus h plus x, right? Negative of a negative. Two x's cancel. Don't forget the limit notation. So we end up with negative h over h. Which gives us negative 1. Okay, so function is differentiable when f of x is positive. Right? When x is positive, it's differentiable. We get 1. When x is negative, we get negative 1 for the derivative. And so what happens is at 0 there's a problem. Right? Because on the right side of 0 we get a slope of 1. On the left side of 0 we get a slope of negative 1. Okay, if we do the limit in which we did earlier in the course, the limit as x approaches 0, right? From the right side it's approaching 1, from the left side it's approaching negative 1. Okay, so if we do, and this is what I'm talking about, the limit as x approaches 0 from the right is 1. As x approaches 0 from the left, it's negative 1. And so at 0, the function does not exist, right? The limit does not exist. So therefore, at 0, we would say this function is not differentiable. Or in other words, function is differentiable at all x except 0. Okay, and then graphically, you guys know what this looks like. Okay, it's a V, right? And so we're going to see that when we see these sharp turns, like these corners, the derivative will not exist at those turns. Okay, there won't be any tangent line that we could draw at a corner. Okay. So we have theorem, if function is differentiable at a, then f is continuous at a. How can a function fail to be differentiable? Okay, so we saw in this example that the function has a corner, okay, or a kink, if there is something like that in a function, the graph has no tangent at this point, and the function is not differentiable there. Okay, other places where the function is failing to have a derivative, if you have a vertical tangent line, that's another place where we don't have a derivative. Okay, the function is not differentiable at those vertical tangent lines. Okay, so vertical asymptote, okay, vertical tangent line in this case, here it appears continuous, but we have a vertical scenario here. Another vertical tangent line here, okay, the function is continuous, but at this point, it's a vertical tangent line, so not differentiable there. Okay, other places that we've discussed earlier, okay, a corner, okay, obviously a discontinuity, okay, like this, anytime it's discontinuous, okay, and a vertical tangent. Okay, higher derivatives. Okay, if f is differentiable function and its derivative is also a function, then we could have a derivative of a derivative. Okay, this new function, we would call it f double prime, would be the second derivative of f. Okay, because it's the derivative of a derivative. Using Leibniz notation, it would look like this. Okay, d dx of dy dx, and you often see Leibniz notation like this. Okay, that would imply the second derivative. Okay, if you're using the f of x notation, you would see f with the double prime. Okay, if f of x equals x cubed minus x, find and interpret f double prime of x. Okay, so let's find f double prime of x. Now we had earlier found f prime of x, right? F prime of x was what? It was 3x squared minus 1. Okay, so then let's use the definition of the derivative and let's apply it to this, and we could use and get our second derivative. Okay, so we'll set it up. So we're going to do f prime. We're going to take the derivative of that. So limit as h approaches 0 of x plus f prime of x plus h minus f prime of x all over h. Okay, so that means we would have, again, limit as h approaches 0, plug in x plus h into f prime, so 3x plus h squared minus 1 minus 3x squared minus 1 all over h. Okay, expand on the x plus h squared first. Okay, so you'll have it like this. X plus h times x plus h, we did that earlier. X squared plus 2xh plus h squared minus 1. We could distribute the minus into the second one, minus 3x squared plus 1. Okay, distribute the 3 into the first parentheses, so we have 3x squared plus 6xh plus 3h squared. Okay, notice we have the minus 1 and the plus 1. Cancel those out. Minus 3x squared. Okay, the 3x squared and the minus 3x squared, they will also go away. They cancel. We could factor out an h with what's left. 6x plus 3h. Cancel out an h from top and bottom. So we have limit as h goes to 0 of 6x plus 3h. Okay, apply the limit, plug in 0 for h, 3 times 0 is 0. So we're left with f double prime of x equal to 6x. Okay. Okay, so comparing the three derivatives now, we got, well, the two derivatives plus the original. We got the original function, the cubic. First derivative is a quadratic. And then the second derivative is a linear function, 6x. Right, so, okay, notice this second derivative would be the slope of the first derivative. Okay, and it's telling us this 6x would be the function for the slope of the first derivative. Okay. Okay, so notice when the first derivative has a negative slope, the second derivative is in the negative. Right, this is in the negative. So that corresponds. As soon as you look at the first derivative and it turns the corner and now has a positive slope. Okay, the second derivative is in the positive region here. Okay, so there's a correlation there. Okay, higher derivatives. Second derivative is a rate of change or the rate of change. The most popular example of this is acceleration. Okay, so generally we defined s of t as the position function. Okay, then we defined the derivative of that position function with respect to time. Okay, ds dt, that's known as your velocity function. And then if we take the derivative of the velocity function, dv dt, that's known as acceleration. Okay, so that's the second derivative of the position. Okay, and that's our acceleration function. Okay, the third derivative, so we could have the derivative of the derivative of the derivative. The third derivative is the derivative of the second derivative. Okay, it can be interpreted as the slope of the curve for the second derivative. Okay, and then the notation for that would be, you would have either y triple prime f triple prime x, or you could have d dx of the second derivative, or you could have d3 y over dx to the third. Okay, and then the nth derivative, you could always write it. Okay, the fourth derivative would be f with 4 primes. Okay, you could also denote it with f and then 4 in parentheses. Okay, and then higher derivatives, you could just put f with the number, okay, inside parentheses. You just won't keep tacking on primes. It would probably get to be a little crazy if you did just kept counting the 5s, but you could put n in parentheses. Okay, and you could write the other versions this way. Okay, if f of x equals x cubed minus x, find f triple prime x, and so the third derivative of x and the fourth derivative of x. Okay, so remember the second derivative of x was equal to 6x. Okay, this is the same problem we had this whole section. And we're just expanding on it. So a second derivative of x is 6x, which is a linear function. So that means we could easily get the third derivative, right, which is the derivative or the slope of this function. Now the slope of a linear function, that's your m, right? So this is going to be 6. Okay, so that part's easy. And so that's the third derivative. So now looking at the fourth derivative, now if we graphed the function of 6, okay, so 6 would look like this. And so if we're looking at the slope of that, that would be the fourth derivative. The slope of a horizontal line, right, the slope of this is going to be 0. Okay, and that's always the case. Anytime we have a slope of a horizontal line, that's going to be 0. Right? Horizontal line always has a slope of 0. Okay, the third derivative of the position function, okay, that's the derivative of the acceleration. That's known as the jerk. Okay, so that would be the notation for it. And then jerk is just a sudden change in acceleration. Okay. So if you're in a vehicle, any abrupt movement, right? Any jerk, that's what we define it as. Okay, the change of acceleration, the rate of change in acceleration. All right, any questions on it? Please let me know. Email me. Okay, bring it up in class. Okay, have a good day. Have a good night. We'll see you soon.